Cool. Hi, everybody. Welcome to week 6. It is July 27th, 2021 of Drexel AI's summer GBM, our 6th one this term. Today we'll be going over some stuff related to our project, related to some emails I've gotten from other clubs, related to the conference proceedings. I will wait for people to come in and then we'll get started. Hi, Alicia.
Hello.
You and I and Michael. Have you met Michael? Michael's in lab.
Was he was there last week, right? The last
Yeah,
meeting.
yeah.
Yeah.
Us three, we should get together to talk about projects
Yeah. Definitely.
when we find time to do that. But yeah, cool. Because I'm sure you'd like to do more than just sit around and listen to people present.
Yeah.
Yeah.
When are you usually free? Or
I am. I'm generally always free before 2 in the morning, before 2.
okay.
I'll text Michael. Maybe we'll see if we're free tomorrow or something. Tomorrow's a Wednesday. Yeah, I'll text him.
Okay.
When are you free?
I can meet tomorrow before 2. I have class until 12 tomorrow, so I can meet then. But also tomorrow I'm going to office hours for my CS assignment at 2:15. So I guess that block would be fine, like 12 to 2.
Okay. Cool. So if other people don't join, we can get started. Might be a small crowd. Adam, what's up?
Hey, thumbs up. Hey, Alicia.
Yeah, okay. So while we're all here, we can talk about a few things. First off, I got emails from 2 people. The first one was Jason Fung talking about, he's from Drexel Steinbright, and he was asking whether we'd like to be put on a list for professional development opportunities, and I said sure. I think my reply was that sounds like an awesome opportunity. So what I assume is they have a list of clubs that are interested in getting in contact with alumni, and they'll reach out to specific organizations that are related to what the alumni are in. So if there's anybody if there are any alumni interested or doing work in AI, we might be able to get in contact with them. And Andy, yeah, it sounds great. Very happy about that. And then we also got an email from Theta Tau. I'm not in Theta Tau, and I'm not at all. I'm just not associated with any of that. So I don't know what they'd want to do with us. But it looks like they're looking less for projects, but more of service initiatives. So instead of IEEE's talking to us about doing some sort of project, right? And I've been emailing with them a bit. They haven't gotten back to my last email when I asked where the event would be for the fall. But Theta Tau wants to do more service, which could be cool. You want to be able to do research and also make sure that your presence on campus is well known, and that's a good way. I think service is one of the good ways we could do that. So I will wait to hear back from them. If you guys have any ideas for service activities we might be able to do, I could go back to them and say, oh, this is what we talked about in our last meeting. If anything comes up, just sitting here today. Otherwise, I'll just wait to see what they have for us. Cool. So I looked into the conference proceedings just before this meeting, actually. I know Safik said he was going to help out. So it looks like there's like two main things that we have to do. One would be gathering the content, which is something that I already attempted. And that is when I reached out to the authors and I said, okay, we want the revised manuscripts back to us by the 19th. And I've gotten all of them. And then we have to do a screen for plagiarism. And I'm pretty sure that they do that internally. But the reason why the content is important is because they have like a if you're like in design, this might be analogous to like an MVP, a minimally viable product. So there's the minimal amount of things you need in order to create conference proceedings, and they define it pretty well. They actually have a bunch of content types here, but I would have to go through this and try to cross it with what information I have, and I might just take up their their statement here. IEEE is ready to help, so I might call them and ask them how do we do this. I explained to them we did a student-led conference 2 months ago, and we were hoping to see whether we could get our conference proceedings in with IEEE, and if we can't do it this year, how could we prepare to do it next year? And that's just something I might have to call them. But regardless, I want to learn. I think it's important for me to learn and all of us to learn together what conferences expect, because that might it might help you when writing papers in the future, because you might know how to shape your paper when you're writing it for a conference, because often conferences kind of just want the same thing in the same format so that it looks pretty and looks this continuity between works. It's part of the reason why we do all of our writing in LaTeX, because it's easy to format it, and there are formats such like IEEE formats. And that's kind of what I've been using. You'll see like IEEE author ref mark. That's because it's an IEEE template. So if no one has questions on that, I want to go on to the progress from last week. So a few of you have actually added a lot. I think that Anch, you did the genetic algorithm, and Savek did the sparse coding bit. I haven't like read it in much detail aside from what Anch you sent me over Slack, but I will definitely find time to go into it. And what I'll end up doing is I'll read it and then I'll leave comments on the document. So if we go down to genetic algorithm, I'll just like highlight this and say, I think if I just like do add comment, this needs to be changed. They'll just show up like this, and you can see that there's a comment by just that right there for anybody working at this document. And everybody who's involved in the project is free to read over and leave comments. Generally, you want the paper to be kind of self-sufficient, so you want to explain it to enough degree that someone with like general background knowledge is able to understand it. For like the audience, the like attended audience, pretend that this paper would be given off to someone else in Drexel AI, so they have an interest in AI. They understand basic themes in AI, like training, testing, models, all that kind of stuff. So you kind of want to shape your you want to shape your explanations in these topics and those different things. So yeah, I'll read over the genetic algorithm, sparse coding. I'll probably add and change genetic algorithms a bit, and then I might add a little bit to sparse coding. I might actually have to talk to our professor, Professor Kim, about that, because I'm not sure how much we should add to that or how much background we need. But looking at the references we already have a good number of them. I know Savek spent a lot of time adding to his, and Ansh, you did a good job. You found 3 of them, which is phenomenal. For the time series forecasting, that's the other big part of this. Alicia, if you have any references that you'd like to include, you can include a paragraph or 2 in there. Anyone else who's interested in like time series forecasting, that as a method we're using, can feel free to add their research in there as well. Eventually, hopefully during this week, I'll be able to flesh out the data sets and at least the data set section and then the network architecture section. Now that I'm thinking of it, what Anch wrote in the genetic algorithm might actually go into 3C, specifically where you mention the number of children, like the definition of these variables, where like genetic algorithm might be more general. But I'll take a look at that and I'll just see how it flows. And then, yeah, this week I'll work on that. And then hopefully the week after we'll be able to have our experiments finalized and be able to write down some observations. I'm sorry. Okay. Just want to make sure that this isn't important. Yeah, we're good. Okay. So, sorry. The next thing I want to talk about is progress I made on this script. So Alicia, thank you for adding the model. This build model function will take different hyperparameters, which are just the inputs here. So inputs is the data itself, and that's used to define the shape of the input layer. And then we have the output size, which is just the number of outputs that we want to use. In our case, it's going to be, sorry, I'm blanking. In our case, the output is just going to be however many points in the future we want to predict. And then the neurons, so, right, this is going to be inputs.shape will be the endpoints here. And then the output shape will just be the endpoints we're trying to predict. Neurons is how many neurons we're going to use. Activation function, which is used in ReLU, default to dropout 0.5. Loss MSE, optimizer atom. So this will build the model, and this is called in the predict forecast function, where we give it the training data and then the weights. And then we're going to call the model. If there are weights, we're setting the weights, training it, predicting it, and getting the new weights from the first layer. And then we're going to return the test. This really should be like test pred. That's not new. That's something I added. Right. Cool. So I think that works out really well. I haven't tested any of this, but I'm kind of just assuming that we don't need the model summary right now. Actually, whenever I do functions, I always add like a verbose. Can't remember if it's capitalized. I always add a verbose because it's good for debugging. Okay. Cool. The other thing I was playing around with was the sparse representation function. The reason it wasn't working last time is because I was reading the data incorrectly, and Ansh and I were kind of debugging that simultaneously. Basically, you need to, in order to read from PhysioNet, the PhysioNet database, you need to use their own library, which is WFDB, maybe waveform DB, and there's this IO record. There's this IO module that has RD record, and that function is what allows us to read in file data from these files. And from this, we're able to get actual data, and it's in a format that we can understand. So if I run algorithm.py, that's funny. Sorry, we got a tabs and spaces issue. So I want to show you the workflow for how I've been doing this. So I assume So basically the data is always downloaded in a temporary directory. This temporary directory is most likely, the data that was downloaded in this temporary directory is most likely not here anymore, just because since I did this, I restarted my computer. But what I can do is I can say load data. So data tempter equals load data. And what it'll do is it'll download all of the data and return it, and return the location of where that data is in the tempter folder. Okay. And then what I can do is I can call that data, I can take that data and push it into the get segments function, and I'll get the xtrain and xtest. And that's actually what I use to generate this figure. Very simple figure. This is 3 seconds of data. It's at 1,000 hertz, which means that for every second there are 1,000 points of data. Very high resolution. And something else we have to decide on what we're doing today, or what we're going to do for the project, is we have to figure out what size dictionary we're going to use for our sparse representation. So dictionary size, I mean, how big should each of our elements be that we're going to use to reconstruct this signal? So for instance, if we had a dictionary that was 500 long, then one of the dictionary elements might be this right here. In my opinion, this is too big because it doesn't capture small variations. What you might want instead is a dictionary maybe 100 points long. So I think that would be like this. You might even want something smaller, like 20 points long. I'm gonna say, like, I like working in powers of 2, so maybe 16 or 32. Because when we get to these large spikes, they rise really quickly. So the first half of the spike might be might only take 16 or less points. So I'm thinking like 32. Let's do 32 size and dictionary. That means that in the sparse representation function, the sparse model will learn. So let's find out where this is. Batch size, patches per image, to figure out which parameter sets the dictionary size right here. So in order to set dictionary size, you actually have to make it you have to figure out how many patches per image there will be. So we figure out how big each sample is going to be as well. So right now, our sample size, there are going to be 50,000 points in each sample, at least for the train sample, and then 100 points for the test sample. I think when Asamu told me about these, told me about this module, they have to be multiples of whatever your dictionary length is. So for instance, I think our train and test might have to be multiples of 32. I'm not entirely sure. But I think that by going with 32 will be fine. This, by the way, takes about 10 minutes for me to download. It's about 1.7 gigabytes of data. So if you don't want to deal with the downloading, what I would do is I would download it and then move the data that's stored in the temporary directory folder to your local machine. That way you can kind of use it persistently. So your computer could shut off and things wouldn't be deleted from your temporary directory, and you can just load it from there. And then you'd pass wherever you moved it to, wherever you moved the data to, as the tempter parameter to load data. Right. Okay. So let's figure this out. So if you want our dictionary filter size. If we want our dictionary filter size to be 32, then that means that our, let me just figure out how many patches per image we have. So we do 50,000 divided by 32. Let's do something even. So maybe 32 times, how many patches per image would we want? I'm trying to figure out how many what should make our sample size. So if our sample size, so if our dictionary filter size was 32, then our patches per image, actually, you know what? I don't like how he did this. Instead, what I'm going to do, sorry. So if we had 64,000 divided by 32, that's 2,000 patches per image, right? So that means that we're just going to change all of this to be a little bit more than what we'd expect, which is fine. And then maybe we just predict out 100. So 32, we can do 128. So just making so that they're both a multiple of 32. Yeah. So this is going to be 64,000. This will be 2,000. That'll give us a dictionary filter size of 32. Batch size is used for training, and then the number of batches is just based off of the number of input samples we have. So we also need to figure out how many samples we want to take. Right now we only have 100, but I think what we can do is we can grab a little bit more than that. I think there's 500 samples in the data. So that means that we might want to just grab this, and that means that we should probably decrease the batch size to like 20. So now we're going to get many more batches. We're going to bet 25 batches because it's 500 divided by 20, which is 25. Yeah. Num filters is the number of units in the activity and dictionary components of the sparse model. These are parameters for sparse learning. I don't know all of them except for alpha because it's labeled. I might add early stopping just so we don't overtrain. I think I can call that I think that's a callback in TensorFlow. It might be included in here actually. Hold up. So yeah, so the module that I'm using from Asamu is actually, it was in his sparse minced GitHub. So if we go to sparse minced it's on its public page, I think. He has this one public repo which has the sparse model applied onto used for the minced data set. I think I showed that, but you know, we're trying to kill time right now because it's loading in. I will just load up Jupyter Notebook and show you it. Does anybody have any questions as I'm going through this? I want to make sure that everyone understands the like thought process behind writing this code and how these things are tying together.
I just have like a general question about the project. So what does Asamu's sparse module do to the data?
Okay.
Like before it runs through the model?
Yeah. So what it does is so he's looking at the MINS data set, so handwritten letters, and the data so it's creating this dictionary, and the model creates this dictionary of filters. And you can kind of see that they represent parts of digits. right? And then what you can do is you can take the actual digit and then use those filters to reconstruct the digit. So this digit is input to the sparse model. Using the dictionary, it uses those patches, those dictionary elements to reconstruct it with only using these components. And the idea is that, right, if you have a good dictionary, you should be able to reconstruct an image to a reasonably good degree. That's what the model does. It kind of struggles with 4,
Right.
but for some of these, it does a pretty good job. And then the hypothesis that I kind of threw out there is if the hypothesis I threw out there is if we get a good dictionary for these first endpoints, we should be able to select the weights that produce the best prediction by comparing the reconstruction. So we're predicting M points, and we're comparing the reconstruction. We're comparing to see how well those endpoints can be reconstructed using the dictionary generated on these first endpoints, right? So
Okay.
let's say, like looking in the digit example, like let's say let's say we're like trying to predict something here. We're trying to like predict the image, which is a really difficult task. We'd say that the weights that predicted this was relatively a bad grouping of weights because it doesn't accurately utilize the dictionary. But this one utilizes the dictionary pretty well, right? So these weights that predicted this image would be higher on our radar, and we'd want to select for the weights that best utilize the dictionary.
Okay.
Yeah, no, good question. Because oftentimes I forget what I'm doing. Yeah, so that all does this, and I'll add the callback. All a callback does. So if you Google like Keras early stopping, it's a function in TensorFlow.callbacks that will stop the training if it reaches some minimum, if it observes that the loss isn't converging for so many iterations. So for instance, min delta is used as the minimum change in the loss. So if there isn't, so when we set that equal to 0, that means that if there's no decrease for some amount of time, it'll stop the training. The amount of epochs that are tracked. So if patience is set to 5, that means that if there's no observed change below min delta for 5 epochs, then that means that it'll stop. I think the way you do that is you just go to, I think it's in fit. It might be in fit or compile. I forget where you put it. It's in fit. Okay. So for instance, what you might do something like this. Nothing's better than copy and pasting code. Enter loss patient 3. And then in fit, you do callback equals. And then what we can do also is we can say TensorFlow stopping. And I don't think I'm in my virtual environment right now, but that's fine. Okay, so right now we have data. data, we have data, which is 100 by 100,000. We recently changed this value though to 500, but we have tempter, right? And this is just the location of where the data is located. This is the location of where the data is downloaded. So if I simply, I think it might work in my browser in here. So if I just click on that link, it'll take me to where the data is located. It's right here. And if I wanted to save this, I could, if I wanted to make sure that I didn't have to download it each time, what I could do is I could just locate a project directory. So I'm just going to my Drexel AI folder. I'm going to make a data directory, physionet.org. It's pretty general, but I'll rename it. Let's say instead of that, let's make it right. Copy and paste this. Make that our tempter, like that. And then what we can do is we can say data. We don't need the temporary directory anymore. Load data tempter. Oh. Sorry. I think I really messed this up. I think that there needs to be physionet.org needs to be inside of the file, right? So that's loading it in, but we're gonna make that n 500. I think it's n samples. Like that. And now it's just going to grab 500 samples from that data directory. At least it should. If it doesn't, I will just use the 100 samples and I'll test this out later. Yeah, so it's definitely, it's skipping this part and then it's just going into each of the files and it's using RD record.
I have a question.
Sure.
So what is the model file for?
The model file is what I was showing you from Osamu. It's his it's what does the sparse coding. It's what generates a dictionary and is able to, it can be used for generating reconstructions of inputs such as images, like I showed you in the Jupyter notebook here. So
Okay.
in the model.py, there is the sparse model class, which extends from a Keras model. So a Keras model, you can kind of think of it like a sequential model, but this is just building on top of it, where it's using so many hidden layers based on certain inputs, and then it does the dictionary learning. This is not what I thought would happen. Let's just do 5, data.shape. Yeah, so it's working. So I effectively what I did is I moved the data from this temporary directory to this directory that's more native to me. You know, I moved it to a project directory. And then I'm able to load in that data, but it just grabbing all 500 for some reason takes a long time, but grabbing 10 works fine. So I'm not going to bother waiting for 5. The next part in the pipeline is getting the training data. So let's format as xtrain and xtest segments. That's the function we want to use. We give it data, and then we want to say n equals 5 and n equals 10 in this case, and train points equals 64,000. And then n test equals 128. We have this and this. Sorry, that's the same thing. Where the first, this is the first endpoints, the 64,000 points are adjacent to the m or 128 points. They're adjacent to one another, right? There's a lot of commented code, but that's because that's some things I was exploring. And now that brings me to this, and I haven't tested this per se, and I don't think I want to on camera because I don't know if it'll work too well. But I'll do that. I'll definitely run the experiment this week and then discuss. I'll test it out. What I'll do is I'll test this out this week, early this week, and then I'll talk in the chat so we can all understand, we can all figure out what we're doing for this function, which I haven't gotten into yet. But does anybody have any questions about what I've been going over so far related to what's in algorithm.py?
I do have another question though. Say that like the results are not what we expected, then like when we put it on our paper, right, it's totally fine to have like that we were incorrect as well.
I think so. There have been some papers that we did this past year for Drexel AI in which the results didn't come out as expected. They weren't as widely received by conferences, but it's still a paper nonetheless. You kind of, part of research I think that most people don't appreciate is you have to figure out what doesn't work. I think that, you know, for me it's kind of like a shot in the dark because it's just an idea I had. But if it does work, it'll be well. But if it doesn't work, then we know that sparse coding can't be used in this way for time series prediction. So what we can do is if we can leverage the fact that we can leverage what we learned from the paper in order to make suggestions that will lead to future works. So in the future work section, we might talk about how maybe sparse coding can work with time series forecasting only if we have a better way of selecting weights. So the weights can be selected in a variety of ways. I wanted to start off with, I thought it was a good idea to start off with a genetic algorithm approach because, you know, if we're doing something that's relatively computationally inexpensive, then that means that we can do many simulations. Oftentimes you need smarter approaches like gradient descent, which works on finding a minimum through the gradient of a function. We don't have that gradient because we're working with a simulation. Oftentimes you can't use gradients whenever you do simulations. Genetic algorithms are more closely related to like Monte Carlo simulations, where you kind of take a function that you don't exactly have, where you have some sort of behavior that you can't exactly map to a differentiable function. So in the future work, we might suggest that maybe it'd be better to try to create a model that would do this prediction outright and then use gradient descent to find the best weights for that algorithm. But that's difficult for the reason I brought up in week one, where when you do predictions for m points trained on n points, you tend to drift and your errors sum, which make it impossible to predict far off in the future.
Yeah, that makes a lot of sense. Okay.
Yeah, no, good question. So yeah, we have the parts individually. So this is so we look at our paper, right? That's not it. It's the other paper. Look at our paper. We have the three main parts in our method section, which is sparse coding, time series forecasting, and the genetic algorithm. The time series forecasting can basically be seen in build model and predict forecast. The sparse model can be seen in reconstruct sparse representation, where you're using Samu's module here. Now, the genetic algorithm is a little more complicated because it incorporates both of those things. So I created this 2 weeks ago, and I haven't looked at it since. So we'll go through it and kind of talk about what we're doing. So for the first, you're basically creating a sparse representation for all of the data in the training set, and then you're finding the number of children for which you want to find. You're finding the number of children you want to use in your top selection criteria. So for instance, if you have n children, 100 children per generation, that's the amount of simulations you're doing, and your alpha is 0.05, then you're going to want n top to be a 5 there. And then for so many rounds or epochs, you're tracking the weights of each child and then the score of each child. And for each child, you're this is not what I wanted to do. I'll have to rewrite this function. This function was written before I created the get segments function. And what the get segments function does is it creates adjacent train and test samples. So instead, what should happen is for each child, sorry, 1 second. I'm trying to think. I'll kind of illustrate what I'm thinking. So for each child, we want to get a score for that child, and that will tell us how well those weights were used to create the prediction, for which we're comparing the sparse reconstruction to. We're comparing how the sparse reconstruction was used relative to the dictionary that was learned by the first n time points. Now, what I'm trying to figure out is whether we want the children for each generation to be the same or different. I think they should be different. And this poses a problem because currently what I'm doing is for each data file, I'm finding a random time point and I'm pulling that out as one sample. So in data, so I have the get data as a load data file. So if we look in data, the first sample in data will be used to form the first sample in xtrain and xtest, which isn't necessarily a bad thing, but the reason why it's not a good thing is because we need many, many, many samples, right? And I think we should leverage the fact that there's so many points in each sample. We should grab maybe like 20 or 100 samples from the first patient file. That way, if we grab 100 per each sample in data, that means we have 100 times as much data in train and test, which means we can effectively randomize. We're basically what I'm saying is I need to grab more than just one region per patient. I should grab maybe hundreds of regions per patient so that we have enough data to generate these scores without replacement. So when I say without replacement, I mean you can kind of think of it as like you're looking at a deck of cards and you're trying to see the probability of picking a card. Without replacement would mean that when you take a card out, you don't put it back. So for instance, for the let's say I have 20 generations and 50 children in each generation. The first generation, I pick a random. I forget what I said. I pick a random. In the first generation, I pick a random k children in the population, and then in the next generation, I pick that population minus k, and I keep doing that until there's no more children left in the population. That way you're not using the same children each time. I don't know what would be the best way with or without replacement, but I have a feeling that you kind of want to get unique children each generation to do the scoring. At least I think so. I'll have to make it so that make it so that get segments retrieves more than just one random time point. I could just add a for loop in here, right? This actually would be pretty easy. Okay, in range. And samples.
Sorry, I have a question.
Yeah.
So do you mean that you're going to take every generation and after that test each child of it and then reduce the number of childs you are testing after every successive generation?
So like you go, what I'm saying I have a population and I'm pulling children from that population, but I want to use unique children each generation is what I'm trying to do.
Okay.
And I want to have enough data to use unique children. That's what I mean without replacement. The number of children each generation is the same. I want the children to be unique. So what I did is I just added a n samples per patient. And what that means is that this will just, I don't even need J here. It's very unlikely that any of these values will be the same. So it's very unlikely that A will be the same across, and that's kind of what determines what data points I'm grabbing. So this will just do this in our case 100 more times. So our data will be 100 times larger.
So can't we shuffle children in one generation?
You could shuffle, but the problem I'm having is I need enough data to shuffle, right? And there's only 517 patient files. So if I grab one sample per patient file, I don't have enough children.
Okay.
Yeah, so that's why I'm saying, okay, let's grab 100 per patient file. So then we have 100 times as much data. So then we have, instead of 500, we have, 50,000. And there's a question here. I know I'm coding on the fly, which isn't always the best thing to do. An if statement as well. Yeah, to check whether they're the same. I'm going to have to do that when we go into the run genetic algorithm in here. But I'll have to code that on my own because I'm not sure that I'll be able to do that live. Cool. Well, we found something, we found an error, and we talked through it, which is good. First, before I do the genetic algorithm, I will make sure that this at least, I know it runs. I want to make sure that it generates, I want to make sure that it's able to do reconstruction. So I'll try to format something similar to what Osamu did. For instance, Osamu, he did this, and I want to do this, but for our signal, which is this right here, just to verify that 32 is a good length for a signal that's 1,000 hertz. And then after that, we'll work on running the algorithm. But generating something similar to this will be the first step in verifying, Andy, that our algorithm has a chance of working. In the meantime, sorry, 1 second. Okay. In the meantime, we have this paper, and there are sections that I'd like to get through. I'll mostly be coding. So if anybody wants to take a jab at the time series forecasting, there's probably people in here who know PhysioNet, the PhysioNet database, better than I do. Honestly, this is the first time I've ever downloaded or used data from PhysioNet. Savek may have used PhysioNet in the past. Ansh, you may have. So let me know. if anybody wants to take a stab at that. The network architecture, that'll be in regards to what Alicia sent me. And oftentimes what we do for this stuff is we create like a table corresponding to the size of each layer. So I think we did this in protein nets from
Yeah, I
the
think
spring
there's a
term.
table. I think there's
Yeah.
a table in the.
So we'd want something similar. We'd want something similar to that. And for people who don't know, there's always like web resources, like a LaTeX table generator. So you can just, create you can just create a table here, and then it'll give it to you in the LaTeX. So don't do this all by yourself. I'd say use a generator. But yeah, for instance, we had a generator. Sorry, we had a different generator. we were doing a GAN model, and we had a generator and discriminator, and you can just have a table that lays out the output shape, the layer type, and the number of parameters, and that's pretty much it. What you need for the model architecture. It's kind of what I'm thinking in terms of the network architecture section. Oftentimes, what people try to do is they try to select hyperparameters that kind of are specific to the problem at hand. So you might want to pick neurons that correspond to like the number, like some value that's related to the endpoints we're using to train on, or something like that. It should be specific. The hyperparameter should be specific to the problem we're trying to solve or the data set. And then if anybody wants to take a stab at the algorithm, let me know. And I'll always read through this when I have time. A bulk of my work will be in experiments and then some in future conclusions, because I'll have to outline how we're modulating, how we're performing this analysis and the shortcomings. That'll be an important part. I know that, was it Andy that already did some work in the limitations? Excuse me. Sure.
Yeah,
Okay.
this morning I also incorporated, like, I put together a quick introduction that I'm gonna add on to as well.
Sure. Oh, you did this today?
Yeah.
Oh, thank you. Cool. It's shaping up, guys. It's shaping up. I like working on things throughout the term instead of all at once at the end. It's actually surprising how, efficient that is. People should do it more. Don't procrastinate. Great. Cool. So I'm done for today. My voice is getting kind of tired. I have a meeting at 4, but I'll be here till then. So if anybody has any questions, let me know. But I appreciate you guys coming. I know smaller group today. We're kind of dwindling down to the core team. But yeah, I hope you guys have a good day. I'll see you next week.
Bye.
See ya.
Ethan, what happened with the robotics team?
Oh no, that's still happening. I emailed them, asked them where do you think it'll be in the spring? No, sorry, in the fall, and they just didn't respond to me. But it's still definitely going to happen. I'd still like for it to happen.
That's
Exciting, right?
Yeah.
Will you be on campus then?
Yeah, in the fall I'm coming.
Okay.
Cool.
Cool.
All right. I'll
Yep.
see you then.
Yep. I'll see you.